In this lesson, we're going to look at two things to do with surds. Firstly, we're going to look at binomial products, and then we're going to look at rationalising the denominators of fractions involving surds. So first of all, what do we mean by binomial products? Well, a binomial term is just a term with two terms in it. So in the same way that, binoculars, bicycle, all these things with that prefix have to do with things that have somehow two. Well, a binomial, something like 5 take 3 root 5. We've got two terms. 5 is one term, 3 root 5 is the other. So if we want to expand a product of two binomial terms, so a product is just multiplying them together. So typically we'll write it something like this, where we just don't bother writing the multiplication sign in the middle. And one way you can do it is using what we call the distributive law, where you just multiply each thing by each thing, and you end up with this. Now, a couple of ways to remember that. There's various drawing ways to remember it. One that I quite like is calling it just crab claw. It kind of looks like a crab claw if you look at these, what you're multiplying. Now, another thing that we want to do is, if we really want to speed this up, some of these products, if we notice some patterns in them, we can really speed this up. And especially the ones that come up most commonly. So we'll just do one where there's no obvious pattern. We'll just do this one, fairly just arbitrary numbers, you might say. But so how do we do this? Well, we just expand with our crab claw. So if you want, you can draw out what looks a bit like a crab claw, and you just multiply the things that have on the arrow. So first we'll do the 3. So 3 times 2 is 6. Then 3 times negative root 3. So we've got to be careful that there's a negative there. So 3 times negative root 3 would be negative 3 root 3. Then we do the root 3. So root 3 times 2 is plus 2 root 3. And then positive root 3 times negative root 3, well, that would be minus root 3 all squared. You might remember, if you have a square root sign and then it's all squared, you just get the number itself. So we get 6. And if you simplify these like terms, these are like surds, so we can simplify. So it's what? We end up with negative root 3. We just minus 1 is the coefficient, right? And this becomes minus 3. So it's 3 take root 3 is our final answer. So there we're just using distributive law, nothing too fancy really going on. Where we want to see these patterns is with the following 3 cases. So one case is where you've got your binomial, so you've got your two terms. We're just keeping it general, calling it A and B. And we've got that all squared. What's the pattern from that? Another useful pattern is noticing when it's basically the same thing, except now we've got a minus sign in the middle. And then the final one is what we call difference of two squares. So you may well have seen this one before, where we've got A plus B in brackets times A minus B in brackets. So if you haven't come across these patterns before, if they don't seem familiar, I would recommend pausing the video and just expanding these by hand using that distributive law. So say with the A plus B all squared, it might be easier to write it out as A plus B in brackets times A plus B in brackets, expand it out, see what you get. And then once you're ready, press play on the video again and you can see me explain the patterns. Okay, so here are the patterns. So here's what happens if you expand it out by hand. You get this, and then if you just look at the answers, so here's all the working, but we don't really care too much about the working. What we care about are the patterns. So do you notice anything about these patterns? For me, the thing that is pretty clear is when we've got one of these binomials all squared, you always get the first term squared and the last term squared, and they're always positive, no matter what's in the middle. And then the sign in the middle just tells you the sign of the thing in the middle. So if it's positive in the middle, it'll be plus 2ab. If it's minus in the middle, minus 2ab. For difference of two squares, you always end up with the first thing squared, take away the second thing squared. So noticing these patterns will just make any problem where we have something like this, which as it happens come up quite a bit, you'll get the answer more quickly. So just for really ease of, just to really elaborate my point, let's just do a quick one where it's just algebra. So say you have x plus 3 all squared. Well, if you want to use this pattern, you go, all right, well, I need the first thing squared, that's x squared. Then I need, it's plus in the middle of that one, so it's plus at the front of this. Then it's 2 times the first thing times the last thing. So it's 2 times x times 3, so that's 6x. And then it's the last thing all squared, so 3 squared is 9. Just an example with some algebra. Okay, so let's just do a couple of these examples where we're actually using surds. So if we're using the patterns, what we can do is with this first one, well, it's the first thing all squared, so it's 3 squared is 9, root 5 squared is 5, so we're going to get 9 times 5 at the front. And it's negative in the middle, so it's minus 2 times the first term times the last term. So it's 2 times 3 is 6. Then root 5 times root 2 is root 10. We're just multiplying the things under the surd. Then we get the last thing squared, and it's always positive, so plus 2. So if you simplify that a bit, you get, so 9 times 5 is 45, plus 2 is 47, and the surd just stays as a surd, 6 root 10. All right, this one, what do we got? We've got it just positive in the middle, so we can use similar patterns. So root 3 squared will be the first bit. We can just, I might just scroll up so you can see those patterns. So it's, this one here, isn't it? So root 3 squared is 3. Plus 2 times the product of those numbers. So 2 times 2 is 4. And then root 6 times 3 is 18. And then the last thing squared. So it's 2 squared is 4 times 6. What's 4 times 6? 4 times 6 is 24. Yeah, sure is. Okay. And then the last one, I might be able to tell this is a difference of 2 squares. Even though it's the opposite, these have been switched around. With multiplication, we don't care about the order. 3 times 5, same as 5 times 3, right? So what we get with this one is we just get the first thing squared, take away the last thing squared. So first thing squared is 14, and the last thing squared is 2. So what, that would be 12. 14 take 2. All right. Okay. So that's it for binomial products. As for rationalizing denominators, let's have a brief talk about that. So if you think about working with fractions, if you ever want to add or subtract a fraction, you need them to have the same denominator. Now, if you've got one of your fractions with a surd as a denominator, it's quite difficult to make those denominators the same. Whereas if we go to the effort of rationalizing our denominators, making them a rational number, typically a whole number, that's going to be much easier when we're playing around with these fractions, maybe adding or subtracting them. The way we do this, the way we rationalize our denominators, is we've got to multiply our fraction by a special factor of 1. The reason we do that, well, let's have a quick look. But we'll have a look at the quick factors of 1 that we're talking about. So if you look at this one, it's got a surd on the bottom, difficult to work with. This one, no surd on the bottom, easier to work with. So if you think about all of these factors, they all look different, don't they? Root 2 on root 2, root 5 on root 5, root 30 on root 30. But we know if you divide something by itself, you get 1. So if you think about if you multiplied any number by one of these factors, would that change it? It would not. All of them are equal to 1, right? And if you times something by 1, you've still got the same thing. You're not changing it at all. So what we have to do is be a bit smart about picking what our 1 looks like, and then we can rationalize our fractions. So if we have a look at these examples, so the factor of 1 I'm going to choose for this first one is if I do root 2 on root 2 and times that together, well, on the bottom, with multiplying fractions, you just times across. Root 2 times root 2 is just 2. And then on the top, you get 7 root 2. And all of a sudden, I've got a rational denominator. Here, similar again, we just look at the denominator, times it by 1, but we times it by 1 such that we're going to get a rational denominator on the bottom. So we do times here. So 3 root 2 times root 5 is 3 root 10. And root 5 times root 5 is just 5. If you can cancel out, do some cancelling, but here, there's no cancelling we can do. All right. Now, it gets a bit more complicated if you've got a binomial on the bottom. So something like this, root 6 take 1 is your denominator. And what we've got to use is use something called the conjugate of that binomial. All we're really doing is if you think back to that difference of two squares, that always involves every part of that binomial being squared. So we'll get rid of any surds. So the way the conjugate works is you just change the sign in the middle of the binomial. And that way, when you're multiplying those things together, you're going to get a difference of two squares. And on the bottom, the surds will disappear, which is exactly what we want. So finding the conjugate is actually quite easy. And then all you got to do, change that middle sign. So for this one, the conjugate of root 6 take 1 is root 6 plus 1. This one, well, it's the conjugate of 1 take root 2 is 1 plus root 2. If this was the other way around, if the numerator were the denominator, because that's a plus, we just put a minus in the middle. So let's have a look at how this works. So if we've got 3 on root 6 take 1, what we want to do is we want to times it by 1. We're going to times it by 1 that is this binomial's conjugate. So root 6 plus 1. So if you do that, on the top, you just get, well, you got to times everything by 3, right? There's some implied brackets here. So 3 times root 6 is 3 root 6. And 3 times 1 is 3. And then on the bottom, you've got here a difference of two squares. So you square the first thing, you get 6, and then take away the square of the last thing. And 1 squared is just 1. So we end up with, on the top, 3 root 6 plus 3 all over 5. Now, I'm actually going to change this problem. I'm going to flip these around just to demonstrate with getting the conjugate all the way around. So we'll forget about this, and we'll do 1 take root 2 over 1 plus root 2, and we're going to rationalize that. So to do that, we got to times it by a factor of 1, where we're using the conjugate of this bottom binomial. So the conjugate is just changing the middle sign. So it's 1 take root 2 and 1 take root 2 on the top. So it's still just, so we're not actually changing the fraction, we're timesing by a factor of 1. And you get, well, on the top, you've really got 1 take root 2 all squared. So we can actually use that pattern from before. So what we do is we get the first thing squared. So 1 squared is 1. Take, what do we got? Take 2 times that. So you get 2 root 2. And then finally you get the last thing all squared, and it's positive, so plus 2. On the bottom, difference of two squares again. So it's 1 squared is 1, take away root 2 squared is 2. So we get, simplify these like terms. So 1 plus 2 is 3, take 2 root 2. And then on the bottom, 1 take 2 is minus 1. Typically, if we've got minus 1 on the bottom, we like to just times everything by minus 1. Just kind of put that through the top, because that's really the same thing. If you divide by minus 1, we're just going to change the sign of everything on top. So you get minus 3 plus 2 root 2, and that'll be the same as being all over 1, which is a bit nicer. We don't have to write the denominator. So it's a bit of a nicer example. Really nice final answer. Okay, that is it for today. Thanks for watching.